Hello and welcome. In this comprehensive lesson, we'll dive into the fascinating world of Integral Calculus 1. By the end of this video, you will be able to define and use integral notation, apply basic integration rules, integrate common functions, evaluate definite integrals using the Fundamental Theorem of Calculus, master the substitution method, understand and apply integration by parts, and solve real-world problems involving area and accumulation. Let's begin by understanding what an integral is. At its core, integration is the reverse process of differentiation. If you know the derivative of a function, integration helps you find the original function. This is why we often call the result of an integration an antiderivative. Let's look at an example. Suppose we have the function f of x equals 2x. We know that the derivative of x squared is 2x, so x squared is an antiderivative of 2x. But is it the only one? What about the derivative of x squared plus 5? The derivative of x squared plus 5 is also 2x. And the derivative of x squared minus 10 is also 2x. This shows that any constant added to x squared will have a derivative of 2x. This leads us to the concept of the indefinite integral. The indefinite integral of 2x with respect to x is x squared plus c, where c is an arbitrary constant of integration. This c represents all possible constant values. Let's break down the notation. The elongated s symbol is the integral sign. The function inside, 2x, is the integrand. And dx indicates that we are integrating with respect to the variable x. So the integral sign, the integrand, and the differential, dx, together form the complete notation for an indefinite integral. Now that we understand the notation, let's learn some fundamental rules of integration. First up is the power rule. This is one of the most important rules you'll learn. The power rule states that the integral of x to the power of n is x to the power of n plus 1, divided by n plus 1 plus c. This rule works for any real number n, except for n equals -1. Let's see it in action. What is the integral of x cubed? Here, n is 3, so we add 1 to the exponent to get 4 and divide by 4. The result is x to the 4th over 4 plus c. Next, we have the constant multiple rule. This rule says that if you have a constant, a, multiplying a function, you can pull the constant outside the integral sign. This makes calculations much simpler. For example, let's integrate 5 times x squared. We can pull the 5 out. Then we integrate x squared using the power rule, which gives us x cubed over 3. Multiplying by 5, we get 5x cubed over 3 plus c. Finally, there's the sum rule. The sum rule allows us to integrate a sum of functions by integrating each function separately and then adding the results. This is very convenient for polynomials. Let's combine these rules to integrate a polynomial. Consider the integral of 3x squared plus 2x minus 7. Using the sum rule, we can split this into 3 separate integrals. Then, we apply the constant multiple rule and the power rule to each term. The integral of 3x squared is x cubed, the integral of 2x is x squared, and the integral of a constant, minus 7, is minus 7x. Don't forget the constant of integration, c. Beyond polynomials, we need to know how to integrate other common functions. Let's start with the exponential function, e to the x. This one is straightforward. The integral of e to the x is simply e to the x plus c. This is because the derivative of e to the x is itself. Next, let's look at trigonometric functions. The integral of cosine of x is sine of x plus c, and the integral of sine of x is negative cosine of x plus c. Remember, the derivative of cosine is negative sine, so we need that negative sign to get back to sine. Finally, let's address the case the power rule couldn't handle. N equals -1. The integral of 1 over x is the natural logarithm of the absolute value of x plus c. We use the absolute value because the natural log is only defined for positive numbers, but 1 over x is defined for negative numbers too. Let's do a quick example combining these. Let's integrate the function e to the x plus 3 times sine of x. We can split this into two integrals. The integral of e to the x is e to the x. For the second part, we pull out the 3. The integral of sine of x is negative cosine of x. So our final answer is e to the x minus 3 cosine of x plus c. So far, we've discussed indefinite integrals, which give us a family of functions. Now let's move on to definite integrals. A definite integral has limits of integration, a and b. It represents a single number, not a function. Geometrically, the definite integral of a non-negative function f from a to b represents the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b. Imagine a curve f of x. The definite integral from a to b is the exact area of the shape under that curve. How do we calculate this area? This is where the fundamental theorem of calculus comes in. This theorem is a cornerstone of calculus. It provides a powerful link between differentiation and integration. The theorem states that if f is any antiderivative of f, then the definite integral of f from a to b is equal to f of b minus f of a. In other words, you find an antiderivative, plug in the upper limit, plug in the lower limit, and subtract. Let's apply this to find the area under a curve. Let's find the area under the parabola y equals x squared from x equals 1 to x equals 3. First, we set up the definite integral. The antiderivative of x squared is x cubed over 3. We evaluate this at the upper limit, 3, and the lower limit, 1. This gives us 27 over 3 minus 1 over 3, which simplifies to 26 over 3. So the area is 26 over 3 square units. Not all integrals can be solved with basic rules. For more complex functions, we need advanced techniques. The first one we'll learn is the substitution method. The substitution method is essentially the reverse of the chain rule for differentiation. It's used when the integrand contains a function and its derivative. The goal is to simplify the integral by substituting a new variable, u, for a part of the integrand. Let's work through an example. Consider the integral of 2x times the quantity x squared plus 1, all to the power of 5. Notice that the derivative of the inner function, x squared plus 1, is 2x, which is also present in the integrand. This is a perfect candidate for substitution. Let's set u equal to x squared plus 1. Now we need to find du. The derivative of u with respect to x is 2x. Rearranging, we get du equals 2x dx. Now we can substitute u and du into our original integral. The integral becomes the integral of u to the 5th power. This is a much simpler integral to solve. Using the power rule, we get u to the 6th over 6 plus c. We're not done yet. The final step is to substitute back our original expression for u. Replacing u with x squared plus 1, our final answer is the quantity x squared plus 1, all to the 6th power divided by 6 plus c. The key to substitution is identifying the u and du parts. Look for a function and its derivative within the integral. Our next powerful technique is integration by parts. This method is used when you have an integral of a product of two functions. It's the reverse of the product rule for differentiation. The formula for integration by parts is derived from the product rule. The integral of u dv equals u times versus minus the integral of v du. The goal is to choose u and dv in a way that the new integral, the integral of v du, is easier to solve than the original one. A helpful mnemonic for choosing u is LIATE. LIATE stands for logarithmic, inverse trigonometric, algebraic, trigonometric, and exponential. You should choose u as the function that appears first in this list. Let's apply this to a classic example. The integral of x times e to the x. We have an algebraic function, x, and an exponential function, e to the x. According to LIATE, algebraic comes before exponential, so we choose u equals x. If u is x, then du is dx. If dv is e to the x, dx, then v is the integral of e to the x, which is e to the x. Now we plug these into the formula. We get x times e to the x minus the integral of e to the x dx. The new integral is very simple. The integral of e to the x is e to the x, so the final answer is x e to the x minus e to the x plus c. Let's try another one, the integral of the natural logarithm of x. This looks tricky because there's only one function, but we can think of it as ln x times 1. Using LIATE, logarithmic comes first, so u is ln x. That leaves dv as 1 dx. If u is ln x, du is 1 over x dx. If dv is dx, v is x. Plugging into the formula, we get x ln x minus the integral of x times 1 over x dx. The x's cancel out, leaving us with the integral of 1 dx, which is x. So the final answer is x ln x minus x plus c. Now that we've covered the techniques, let's explore some applications of integration. One of the most direct applications is finding the area between two curves. If you have two functions, f of x and g of x, and f of x is greater than or equal to g of x on an interval from a to b, the area between them is the integral of the top function minus the bottom function. The formula is the integral from a to b of f of x minus g of x dx. This is the area of the region bounded by the two curves. Let's find the area between the parabola y equals x squared and the line y equals x. First, we need to find the points of intersection by setting the functions equal to each other. X squared equals x. This gives us x equals 0 and x equals 1. These will be our limits of integration. On the interval from 0 to 1, the line y equals x is above the parabola y equals x squared. So our integral is from 0 to 1 of x minus x squared. The antiderivative is x squared over 2 minus x cubed over 3. Evaluating from 0 to 1 gives us 1 over 2 minus 1 over 3, which is 1 over 6. The area is 1/6 of a square units. Another key application is accumulation. If you have a rate of change, integrating it over an interval gives you the total change or accumulation over that interval. For example, if v of t is the velocity of an object, the integral of v of t from t1 to t2 gives the total displacement of the object during that time. Let's say the velocity of a car is given by v of t equals 3t squared plus 2t. We want to find the total distance the car travels from t equals 1 to t equals 3. We integrate the velocity function from 1 to 3. The antiderivative is t cubed plus t squared. Evaluating at the limits gives us 36 minus 2, which is 34. The car travels 34 units of distance. Let's recap what we've learned today. We started with the definition of the indefinite integral as an antiderivative, including the constant of integration, c. We then covered the fundamental rules, the power rule, constant multiple rule, and sum rule, and integrated common functions like exponentials and trigonometric functions. We introduced the definite integral as the area under a curve and learned how to evaluate it using the Fundamental Theorem of Calculus. Finally, we explored two powerful integration techniques: substitution, which reverses the chain rule, and integration by parts, which reverses the product rule. We also saw how to apply these concepts to find areas and solve accumulation problems. To solidify your understanding, here are a few practice questions. Pause the video and try to solve them on your own. Here are 3 problems. The first is a basic indefinite integral. The second is a definite integral that requires substitution. And the third is an integration by parts problem. Welcome back. Let's go over the solutions. For the first problem, we use the power and sum rules to get x to the 4th minus x squared plus 5x plus c. For the second, we use substitution with u equals negative x squared. The result is 1 minus 1 over e. For the third, we use integration by parts with u equals x. The answer is negative x cosine x plus sine x plus c. I hope this comprehensive lesson has given you a solid foundation in Integral Calculus 1. Keep practicing, and you'll master these concepts in no time. Thank you for watching. Let's recap what we've learned today. We started with the definition of the indefinite integral as an antiderivative, including the constant of integration, c. We then covered the fundamental rules, the power rule, constant multiple rule, and sum rule, and integrated common functions like exponentials and trigonometric functions. We introduced a definite integral as the area under a curve and learned how to evaluate it using the fundamental theorem of calculus. Finally, we explored two powerful integration techniques: substitution, which reverses the chain rule, and integration by parts, which reverses the product rule. We also saw how to apply these concepts to find areas and solve accumulation problems. To solidify your understanding, here are a few practice questions. Pause the video and try to solve them on your own. Here are 3 problems. The first is a basic indefinite integral. The second is a definite integral that requires substitution. And the third is an integration by parts problem. Welcome back. Let's go over the solutions. For the first problem, we use the power and sum rules to get x to the 4th minus x squared plus 5x plus c. For the second, we use substitution with u equals negative x squared. The result is 1 minus 1 over e. For the third, we use integration by parts with u equals x. The answer is negative x cosine x plus sine x plus c. I hope this comprehensive lesson has given you a solid foundation in Integral Calculus 1. Keep practicing, and you'll master these concepts in no time. Thank you for watching.